Hey guys, it's Miss Johnson, and I'm here to bring you the second part of chapter 7.3. Today we are talking about the central limit theorem. So maybe you're wondering, or maybe the thought has crossed your mind, all of these calculations are great and good for normal distributions, but what if a distribution isn't normal? Then what do we do? So we're going to talk about the central limit theorem today that is going to tell us how we can work around that scenario. So I first want you to take a look at this picture. So here's a picture of three different populations in your sample size. So it's three different populations. You're taking a sample size of n equaling 2 and then also a sample size of n equaling 25. So these are populations that are not normal, okay? And in fact, there's a lot of populations in the world that are not normal. There's a lot more that are not normal than are normal. So here's just a couple examples. This parent population right here happens to be uniform. This is a uniform distribution. So when you look at the sample data, if you've got a distribution of sampling means where n is equal to 2, your uniform distribution turns into something that looks kind of symmetric. I wouldn't call that normal because it's got a really, even curve there. It's almost like it's absolute value curve. But anyways, it's still symmetric. I would still say there's a peak in the middle. But when you increase the sample size up to 25, now take a look at your distribution. Now it starts to take on a little bit more normal tendencies. So when you're looking at sampling distributions and you increase your sample size, you tend towards a normal curve. Let's look at the second one. In this one, you've got a parent population that is skewed right. Okay, so this was uniform over here. This one is skewed. So with a parent population that's skewed to the right, take a look at what happens. When you take a distribution of sample means that are size 2, your samples are size 2, take a look at your sampling distribution graph. It still holds on to a little bit of that skew, but it definitely is losing the dramatic curve of the skew. Now increase your sample size to 25 and take a look. Check out that sampling distribution. When you increase your sample size up to 25, your sample means tend to go towards a normal distribution, even though it started skewed. Then take a look at this. This is bimodal, if you will. It still looks symmetric, but I would call this bimodal. It's got two strong peaks there, and they're very separate. There's a very clear split in the middle. So let's talk about samples of size 2. If you take the mean of samples of size 2, look how your bimodal distribution becomes trimodal. So you've got, all of these samples of size 2 means that you pulled 2 from this side. All of these samples of size 2 means that you pulled 2 from this side. These ones in the middle means that you pulled 1 from each. When you pulled your sample, you got 1 from the left side and 1 from the right side, which gave you a mean in the middle. So we got a trimodal distribution here of our sampling means. But now increase that sample size to 25 and take a look. Boom. Much more normal. Okay? So here's our point of the central limit theorem. When you take an SRS of a size n from any population with mean mu and finite standard deviation sigma, the central limit theorem states that when n is large, the sampling distribution of the sample mean is approximately normal. So there's your key. Central limit theorem tells you it doesn't matter what shape your parent population is. If you pull a sample size that is large enough, then you are going to get a sampling distribution that is approximately normal. Okay? So what is the definition of large? What does large enough mean? So there's a couple of points here. This first point's pretty easy. This is basic. It says population distribution is normal. Sampling distribution of X bar will also be normal. We've already talked about that. If the population starts normal, then your sampling distribution is also going to be normal. Great. Okay, cool. Move on. The second point right here is the one I really want you to pay attention to. If the population distribution is not normal, the sampling distribution of X bar will be approximately normal when the sample size is large. Most of the time, our magic number is 30. We want our sampling distribution to be above 30. That picture that we just looked at on the previous slide had sampling distributions of 25, and you can already see that at 25, they were trending towards normal. So 30 is a lot safe. 30 is like a safe zone for us. It's being a little bit more conservative because even when we get to 20 or 25, they already start to look normal. So 30 is conservative. That's a safe number. It says if the sample size is small and the population distribution is not normal, the sampling distribution will retain some of the characteristics, for example, skewness. And we saw that in our parent populations. When we looked at the skewed population, when our n was equal to 2, it was still slightly skewed to the right. When we looked at that bimodal population and n was equal to 2, we ended up with a trimodal population. So we still didn't get to that unimodal, which is the goal. We want only one peak. And even more than that, we want it to be normal. So anyways, central limit theorem, basically the key of the central limit theorem is have a sample size that's large enough. So let's take a look here. It says Keith is a manager of an auto care center based on service records from the past year, the time in hours that a technician requires to complete a standard oil change, and inspection follows a right skewed distribution with mu equaling 30 and standard deviation equaling 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem their offer in the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? Okay, so he's budgeting 35 minutes per customer. His mean is 30 minutes. And the question is that enough? Or is he going to need more? So here's how we're going to tackle this. First of all, we need to calculate the probability. We need to see what's the probability that a sample of 40 customers has a mean that's greater than 35 minutes. Okay, that's what's happening in part A. Calculate the probability that the average time, that tells you you're looking at sampling means, it takes to complete the work exceeds 45 minutes. Okay, so here's what we need to know. We need to know, first of all, our sample mean is going to equal our population mean because that's just by definition. So the mean of our sample is going to equal the population mean, which is 30 minutes. Great. How about that standard deviation? So standard deviation of the mean is going to equal the standard deviation of the population divided by the square root of n. Okay? Talk about your 10% condition. So you can keep going and calculating this, but I'm also going to pause for a second and talk about my 10% condition. So it's safe for us to assume, our sample size is 40. So we can say, assuming 40 is less than 10% of all current customers, then the 10% condition is met. Okay, so 20 divided by the square root of 40. Now, again, when you are thinking of that 10% condition, sometimes you just have to go with the assumption. Do we know that he has more than 400 current customers? No, we don't, but we can assume. I mean, if you think about running a mechanic shop, how many cars do they see in a day even? Then add up all those people that they see in a month. And a lot of people don't even go every month to have their car serviced. Usually you're going every, 3 or 4 months to have your oil changed. So it's probably safe for us to assume that he has more than 400 customers. So I'm going to take that 20, I'm going to divide it by the square root of 40, and I get a standard deviation of 3.16. Okay, so there's my mean, there's my standard deviation. Now I need to calculate the probability. So here's the next thing that we have to state, because this is where the central limit theorem comes into play. And you don't have to actually write this, but I'm just showing you that that's where I'm getting this. I'm getting this from the central limit theorem. So here's what you do need to write. Because the sample size is large, or in other words, 40 is greater than or equal to 30, the distribution of means, distribution of sample means, is approximately normal. Okay, now the question is, why did I need to say that? I needed to say that because it explicitly told me in the question, in the original question on the previous slide, that the distribution was right skewed. The distribution of times that it takes for his mechanics to do the oil changes is right skewed, which makes sense to me. There's probably way more customers who take around that 30-minute mark, but then I bet there's still a handful of cars that it's like, oh, this one was a struggle, or I had more problems with it, or it was harder for me to get this XYZ. So there's probably a handful of cars that they work on that are just going to take them a long time for whatever reason. The make of the car, the model of the car, the type of the mechanic, whatever. It makes sense to me that it's a right skewed distribution. But the fact that it's a right skewed distribution is what necessitates us to acknowledge this. We have to acknowledge the fact that our sample size is large enough so that we can use approximately normal calculations when we are looking at the sample means. Because now we're looking at a sample mean, we're looking at a sampling distribution of means. We're not just looking at the parent population. So as long as our sample size is large enough, then we're okay and we can use normal calculations. All right, so moving on. Now we can actually do the work. So here we go, and we're going to actually find the probability. So I'm going to go ahead and guess that most of you will use normal CDF, and that's okay. You're allowed to use normal CDF as long as, are you sick of me saying this yet? As long as you label your values. Some of you still don't do it, so I hope you're hearing me when you say it. So your lower limit's going to be 35 because he wants to know what's the probability that it exceeds the 35 minutes. So 35 is my lower bound. My upper bound is that positive infinity, and you can just put positive infinity. My mean is 30, and my standard deviation is 3.16. So now I'm going to go ahead and type that into my calculator, go to second distribution. Normal CDF is the second option down. I've got 35. I've got an upper limit of positive infinity. My mean is 30. My standard deviation is 3.16. And I paste that, and I get a probability of 0.057, we'll call it 57. 57. Okay, so what that means is about 5% of the time, 5.5-ish, close to 6. You know, somewhere between 5 and 6% of the time, he's above that limit, okay? That's what that means. So now let's take a look at part B, okay? Because what happens is, what if he doesn't want to be above that limit 5% of the time? You know, he's budgeting 35 minutes per customer, but what if going over that limit, going over that 35 minutes 5% of the time is too much for him? What if he only wants to go over that limit 1% of the time? Okay, so it says, how much average time per customer should Keith budget if he wants to be 99% sure that he doesn't go over budget? So basically, he wants to take that 5% that's over the time budget and bring it down to 1%. Okay, so what do we do with that? So now you're kind of doing an inverse norm here. Here's your table. I'm going to draw out a table for this one. I probably should have drawn out a table for the last one as well, but I didn't. But we used our normal CDF and we labeled our values, and as long as you label your values, then you're good. I am going to draw a table for B though. So here's my, or not table, but you get what I'm saying. I'm going to draw a curve, draw the normal curve. Okay, so here's my normal curve. I've got a mean of 30, one standard deviation is 33.16. Subtract one standard deviation, I'm at 26.84, and so on and so forth. So we want to know what would, say, like this value be. What's my x? X is my question. So that this whole piece is 99%. okay? We want 99% of his customers that are coming in for that free oil change to be under the budget, okay? So what does the budget need to be? This is our magic number. What does the allotted time need to be? So in your calculator, we've already defined, by the way, we've already defined the mean, we've already defined the standard deviation, we've already talked about the 10% condition, we've already addressed the fact that we can use the central limit theorem to use normal calculations since our sample size is above the 30. So we don't need to go through and define all those things again. All we need to do is look at inverse norm. So in your calculator, this is an inverse norm question. You're going to do inverse norm. And the three things that you need are the area, which in this case is 0.99, and then your mean and standard deviation. Mean is 30, standard deviation 3.16. Okay, now I want to talk about this area. This is to the left. Okay, if you were asked to go in the other direction, you would have to do 1 minus. We're already measuring to the left because we want 99% to be underneath the limit, underneath the budget, the time budget. So we're already going to the left. If you were asked what goes over, you need to make sure you take 1 minus. If you have a TI-84 CE, one of the newer calculators, if your calculator says CE on the top, then inverse norm is going to ask you what side. So we need to do 0.99 to the left. So if your calculator is asking you what direction you're going in, that's the direction you're going in. If you have an older calculator that doesn't ask you that direction, your calculator always goes to the left. And if you needed to go to the right, you'd have to do 1 minus whatever the area is to get the area to the left. Okay, carrying on. So I'm going to type that in. By the way, all of this stuff over here is really important. And again, I probably should have drawn a curve for part A, but it's okay. We're just going to move on. As long as we labeled our values, that's good. But it is also really nice for the AP exam people who are reading your test to see that you drew the curve. So go into your calculator, second distribution. Inverse norm is option 3 on my calculator. And then I'm going to do 0.99. And I'm going to do 30. And I'm going to do 3.16. And plug that in. So my value that I get here is 37.35 minutes. Now, we can mark it as 37.35 minutes. He might want to round that to the nearest minute, but he could leave it that way. I would for sure write a concluding statement here. So my concluding statement might look something like this. So to be 99, I'm writing a percent sign too early. I turned that 9 into a percent sign almost. To be 99% sure he has budgeted enough time Keith should plan for an average of 37.35 minutes. There you go. There's my concluding statement. Okay. So we did an example here. We talked about using normal CDF, and we also talked about inverse norm. So those are just kind of good review concepts for us. The biggest thing that I wanted you to get out of this lesson today is to recognize that parent populations may not be normal, but that doesn't mean we can't proceed. As long as we get a sampling distribution of a sample size that's larger than 30, the central limit theorem allows us to proceed with normal calculations. That's our biggest takeaway from today. So thanks for tuning in today, and I will catch you next time.